this movie, we use this old exam question to help us to remind ourselves about some concepts about equilibrium, as well as to get some practice with calculations pertaining to equilibrium. Click on that link there to remind yourself about what equilibrium is. Very briefly, equilibrium is the state of a reaction where the forward and reverse reactions occur at the same rate, and therefore the concentrations of reactants and products do not change over time. And we're told that we have a situation with carbon reacting with carbon dioxide to form carbon monoxide gas, and we're given some information about the amount of carbon dioxide gas that is sealed in a container of volume 3 decimeter cubed. And then we're told that once equilibrium is reached, we're given the concentration of the carbon dioxide gas that is found. And we have to find out, first step, what the Kc value of this particular reaction is. So how are we going to solve for that? Well, let's start off by just seeing where are we heading. We're heading to finding out the Kc value for this particular reaction. For this particular reaction, Kc would be the carbon monoxide's concentration at equilibrium raised to the power 2 because of the coefficient 2 there. So we need to find out carbon monoxide's concentration at equilibrium. So you can see here, I've prepared a table. We're going to give the reaction ratio because everything is determined by the way in which these react, the molar reaction ratio. And then we're going to discuss the mole values initially for each of these that are relevant, the change in values, and the equilibrium mole values. But really what is needed for this particular question is not the mole values, but the molar, the concentration values, mole per decimeter cubed, which is molar at equilibrium. And we will need to find out what that value is. We're going to put that in there in order to get the Kc, divided by the molar concentration, which actually we are given right in the question, so that's not a problem, of carbon dioxide not raised to a power, well, raised to power 1. And we do not include carbon's concentration. It's not relevant because it's a solid in this Kc value. So the first thing we need to determine is what that value is there. How do we do that? Well, let's start, of course, by putting in the information that we know. And we know that at equilibrium, carbon dioxide's concentration is 0,054 molar. And what we are trying to find out is carbon monoxide's concentration at equilibrium. How do we find that out? Well, at the beginning of the reaction, initially, there isn't any carbon monoxide present. So all of the carbon monoxide that appears by the equilibrium point came from the reaction. And we can figure out how much that is because we know the reaction ratio and we're given some information about carbon dioxide. And so from that we can see the equivalent amount of carbon monoxide that would have reacted. So, what information are we given about carbon dioxide? A little more than what I've already written down. One is, we're given how much carbon dioxide is in the container right at the beginning. We're given that in mass. So let's convert that mass that we're given into its equivalent number of moles for the initial amount of carbon dioxide. We know that the number of moles is equal to the mass, which is given 60,8 grams of carbon dioxide divided by the molar mass of carbon dioxide, which is 44 grams per mole. 1,38 moles. Keep that on your calculator. We'll use it again. Maybe let's store it into variable A. Shift, recall A, in other words, store A. Right, so what does that mean? That means that's how much we have at the beginning. But that doesn't directly tell us how much carbon monoxide is going to be produced, because it doesn't necessarily all get converted into carbon monoxide. Well, never mind necessarily. We know that it doesn't, because at equilibrium we can see that we have some carbon dioxide still there. And so we need to find out the change, because from the change in carbon dioxide, we can find out the equivalent, the stoichiometric change in carbon monoxide. So we need to convert this amount that we're ending with, which is at the moment in moles per decimeter cubed, molar, into its equivalent amount of moles, and then compare that with how much we started, so that we can see the change in carbon dioxide, from which we can work out the change in carbon monoxide, from which we can find out the equilibrium amount and concentration, which is what's needed over there. So here we have the concentration of carbon dioxide. We want to find out the number of moles at equilibrium that corresponds to that. And we know that the number of moles is equal to the concentration multiplied by the volume. Now you must just make sure that your units are correct. Otherwise you maybe need to do a conversion. So let's check, do we need to make a conversion for our formula here to apply? This unit here is molar, mole per decimeter cubed. So we must multiply it by volume in decimeter cubed, so that the decimeter cubes cancel between the two variables and we're left with moles. And we are given the volume in decimeter cubed. So in this particular case, we don't need to do any conversion of units of volume. So all we need to do here is multiply this 0,054 molar, and I'm going to give it in the unit mole per decimeter cubed, which is the same thing as molar, to make it clearer how the units cancel. And the volume we're given is 3 decimeter cubed. Notice how the decimeter cubes cancel. We're left with the moles. 0,054 multiplied by 3 is 0,162 moles. So what this is meaning is that we started with so much, 1,38 moles of carbon dioxide, and we ended with only 0,162. So what's happened to the difference? The difference has been converted into carbon monoxide. So it's very relevant what that difference is, because if we know what the change was, then we can work out the stoichiometric equivalence of the carbon monoxide that was produced from it. So it's a very simple calculation, 1,38 minus 0,162. And we know that this change is a negative, meaning it's decreased that much. So in other words, we need 1,38 plus this number, which will be a minus, must give that value there. So we still have this value on our calculator, and this one we have stored in memory. So we say that, change sign answer, plus recall A. And it gives us 1,219, let's write 1,22, but let's keep it on our calculator, moles. And you can check that plus that, in other words, that minus 1,22 does indeed equal that value there. So how does this help us? We're trying to find out the equilibrium concentration of carbon monoxide. To do so, we need to find out how much carbon monoxide reacted, how much was produced. Where does it get produced from? It gets produced by carbon dioxide reacting. How much carbon dioxide reacted? This much. So what would the stoichiometric equivalent of carbon monoxide be from this amount of carbon dioxide? To help us figure that out, we have to know the reaction ratio in this equation. And that is extremely easy to see because it's simply given by the coefficients in the balanced equation. 1 mole of carbon reacts with every 1 mole of carbon dioxide to produce 2 moles of carbon monoxide. So that means that twice as many moles of carbon monoxide are produced as carbon dioxide that reacts. And we know that this is how much carbon dioxide reacted, so twice as many moles of that was produced. This is a minus because it's a reactant. This is going to be a plus because it's a product that's being produced. So we know that 2 times 1,22 moles of carbon monoxide was produced. Remember, where are we heading? We're heading towards finding the concentration of carbon monoxide at equilibrium. For that, we need the number of moles of carbon monoxide at equilibrium. This is the change in carbon monoxide. So we need to then figure out, well, how much at equilibrium, and that is really easy because it started with nothing and then added this amount. So that's how much we have. We can do our actual calculation. 2,44 moles, simply multiply that by that, of carbon monoxide at equilibrium. But remember, we need the concentration, so we must convert the number of moles to the concentration by dividing the number of moles by the volume, 3 decimeter cubed. 2,44 moles divided by 3 decimeter cubed. Now, in fact, it isn't 2,44. Let's rather use the value that we have on our calculator. We have the value of this on our calculator, and let's multiply that by 2, and then divide that by 3. And we get 0,8132. Let's keep this particular value because we're going on further. Right, so now we're ready to actually calculate what we were asked. 0,81 squared divided by 0,054. We have this value on our calculator, so let's simply square that and then divide by 0.054. And our answer is 12,25. Kc is dimensionless, so we don't give a unit. Now we're asked the minimum mass of carbon that was needed for this to occur. So we come here to our reaction, we can see that the stoichiometric equivalence is 1 mole is to 1 mole is to 2 moles. We've seen that we need 1,22 moles of carbon dioxide to react, and therefore we also need 1,22 moles of carbon to react, so there must have been at least 1,22 moles of carbon at the beginning. That would be the minimum, then all of it would react. Any more than that would just be in excess afterwards. So what this question is really asking is what is the mass of 1,22 moles of carbon, and we know that the molar mass of carbon is 12 grams per mole. So it's really very simple. So we're being asked the mass of 1,22 moles of carbon, and we know that the molar mass is 12 grams per mole. You can see that the moles cancel, we're left with grams. Now it isn't actually 1,22, so better to use the variable that we actually have on our calculator, which was stored in variable b, and we multiply that by 12, and we get the answer 14,64 grams. And before we go, have you already liked? Have you subscribed? Have you left me a comment? And please go and visit my website. You'll find a lot of resources there, and they're categorized in a way that will make it very easy for you to find what you need. Until we meet again, learn science!